Postdoc at Northwestern. Can you all hear me? Okay, perfect. So some of the goals for this lesson are learning about match filtering. We sort of touched on something very similar when Brian was talking about optimal filtering on Monday. And then we'll talk about how we can do detection with match filtering. That's going to take the first hour of this session. And then when we come back from the break, we'll talk about template banks and gravitational wave detection with match filtering. And that will be a more hands-on session. So I'm going to try to do match filtering in a very general way, because this is actually a technique that's useful in a lot of cases where you have a good understanding of what your signal might look like. Okay, and the question that motivates a match filter, motivates match filtering is how do we detect a weak signal in data that's noisy? So consider noisy data that probably has some signal or might have some signal. We can write the data S of x as a sum of a noise term and a signal term. So it's a linear summation. And this is usually a very good model in astronomy, right? Where noise is usually terrestrial or instrumental, whereas signal is coming from some place far, far away. So they're a linear summation. N is, as I said, it's instrumental noise. H is a signal whose morphology we understand reasonably well. For example, gravitational waves from two inspiring black holes, or pulsar timing profiles whose pulses are relatively uniform. That should be exoplanet transit, of course. Exoplanet transit morphology, the dips that they cause the luminosity of their parent star. And in general, the noise can be much larger than the signal itself, the magnitude of the noise. And in cases like this, most other general detection techniques have a really hard time picking up a signal, picking out a signal. We are sort of dealing in regimes where your SNR is going to be relatively small. Maybe you'll have an SNR of 10 or 20 or something. In a lot of astronomy applications, we have SNRs that are really high, in which cases we don't need something that's as powerful and honestly computationally expensive as match filtering. But in regimes where your SNRs are lower, this method is going to shine. And so it turns out that in cases like this, under some assumptions, match filtering is actually the optimal way to dig out a signal, as we will see. And just one final note, X here it can be any data coordinate. In all of the examples that I gave there, X is clear, X is time, right? But it doesn't have to be time. It can be any data coordinate, it can be frequency. You can work on your photodetector pixel position, anything like that. So what are I just mentioned assumptions. What are the assumptions that we're going to be making? Stationary noise is the first assumption that we're making. Random process, which has a mean and an autocorrelation function that are time independent, is called stationary. Is stationary in sort of the weak sense, right? So what that means is if you take the noise itself as a function of time, or x, as I was using in the previous slide, its mean is constant, and its autocorrelation function, which is the expectation value of this product, depends only on the time lag between the two points of noise that you're considering. And this mean it doesn't depend on absolute time itself. When you have a noise process which is stationary in this sense, then there is this theorem called the Wiener-Khinchin theorem, which relates the power spectral density of the stationary process with its autocorrelation, right? So this is the one-sided power spectral density. What that means is it's defined only for my which means it's only defined for positive frequencies, and this is related to the Fourier transform of the autocorrelation function. Another way to say this is that this cross-correlation matrix between noise at two frequencies. So if you take the noise itself and take its Fourier transform, and if you define this sort of cross-correlation, this vanishes in all cases except when f is equal to f prime. Okay, so far so good. Any questions? Okay. And if you are curious, there's some fine prints to this. Ask me about that later. There is an alternate definition of stationarity which follows from sort of this definition, which is to say that the PSD itself does not change with time. Okay. Just as we just said, with the stationary Gaussian noise, the statistical properties of the noise in the time domain, namely its mean and its autocorrelation function, are sort of enough, are constant with time. And if you consider stationary Gaussian noise, then these two properties are enough to actually characterize the noise itself. All other higher movements sort of vanish. You can make a statement that is equivalent in the frequency domain by saying that the distribution of the noise in the frequency domain is a complex Gaussian with the PSD as its variance. Usually, we can also assume the mean to be 0, which is fine. It doesn't really change your statistics. And in that case, you can model the noise as a complex Gaussian in frequency domain, and this is sort of what it looks like. So n of f is now complex because we are working in the Fourier domain, and so its absolute value is a Gaussian whose and the variance of the Gaussian is basically meant by the PSD. Okay, so that's all background. So how do we use that to do match filtering? Let's go back to, yes, question.
Just for clarification, isn't the Fourier transform or the Fourier transform of a Gaussian still a Gaussian? So if you're saying the noise in frequency space is Gaussian, does that mean in time space it's also Gaussian?
Yes, that is. It is Gaussian, which is why we call it stationary Gaussian noise. But the difference is in frequency space, it's a Gaussian with the PSD as the variance, right? Whereas in the time domain, you have an autocorrelation function, which means that the covariance in the time domain is not diagonal, right? Whereas in the frequency domain, because the noise is stationary, the covariance matrix actually the matrix, it turns out, it factorizes in such a way that it is diagonal. So you can deal with each frequency bin independently, which you can't do in the time domain. You can't treat each point in time independently. Okay, so this is all background, as I said. So let's use this to do some match filtering. So let's consider some filter k of x that we want to multiply. I'm sorry, I'm changing notations here. Let me quickly change this to this. So let's consider some filter which we are multiplying our data with, called k of x, and we are sort of integrating over this. Over the time parameter. Then the question that we want to ask with match filtering or linear filtering, as it's sometimes called, is what is this filter function k of x that will maximize the signal to noise ratio of the statistic s hat? Okay, so we want to for a given filter function to calculate the signal to noise ratio, we need to calculate both the numerator of the signal and the denominator, right? So let's calculate the numerator. The numerator is simply the expectation value of this statistic, right? And since k is just some deterministic filter, the expectation value of this filter is simply the integral of the expectation of the signal itself, along with multiplied with this filter function. So the expectation of the signal, the expectation of the data, which is this is s of x, is the signal itself along with the expectation of the noise, and the expectation of the noise is 0. Okay, so there's something very subtle I'm doing here, which is that h of x doesn't have an expectation value, right? You see, only n of x has an expectation value, or these angular brackets. Why is that? Why does the expectation value symbol doesn't carry over to the h of x term? Yeah, but so you're almost there. So yes.
That's because we're choosing our h of x to be a well-defined function that we already know the value of. So we choose the mean to be equal to the function at that point itself.
Yes. So in other words, putting that in other words, this is exactly what you said. This is because this expectation is an expectation over ensembles. It's not an expectation, or it's not an average over time. If you average h of x over time, it's obviously going to have some value that's not gonna, because h of x in principle could be a changing signal, right? So it could have a value that's different at each point in time. But what we are doing here is not, this is not a time average, because this integral is already in some sense the time average. What we are doing here is an ensemble average, where we are picking different realizations of the data with the same signal and saying, what is this filter function that's going to maximize this, the signal to noise ratio? And when we have different realizations of the data, since the signal itself is deterministic, there is the expectation value of h of x is the same thing as h of x itself. So that's the numerator. And this term, by the way, is vanishing because we just assumed that the noise is a Gaussian process or a stationary Gaussian process with 0 mean. The noise is the denominator is the variance under the assumption that h is 0 or h of x is 0, right? In which case this term vanishes because it's the mean of the noise, and so we are left with this term, which you can use this to expand it out as a double integral times n of x times n of x prime, which gives you an autocorrelation function multiplied by these filter functions. Okay, I know this is kind of getting a little bit too heavy on math, but we're almost at the end. So again, we are using we are defining the statistic, and we are working with the statistic, and we're asking the question, what filter function maximizes S of x? So now I've put together both the numerator and denominator to give an actual expression for S over n. Let's now take the Fourier transform, and we are going to use this beautiful property of the noise that it's a stationary Gaussian process, and use the Wiener-Kitchen theorem to write this expression in frequency domain like so. So h of f now is the Fourier transform of the signal. K star of f is the Fourier transform of the filter function, and the S of f is now the noise PSD, and K of f is, yeah, it's again the Fourier transform of the filter function. And one final thing we can do is we can realize, so now again this is the expression that we have in the Fourier domain. We can define this U of f thing which is given by half S of f times k of f. So this is going to look a little mysterious, but if you sort of work this out, what this means is you can write your signal to noise ratio as an inner product between u of f and h of f, where we define the inner product as the integral between two, as basically the product of the two functions and integrate over that. So since this is an inner product, right? The function that the vector, if you have one vector and want to ask, okay, what is this other vector that I can multiply this with, that so that the inner product between the two of them will be maximized, right? Obviously, that is, or clearly that is the same vector itself, right? So if you have u times v, that would be uv cosine theta uv, and the term that maximizes this inner product would be, or the vector v that maximizes this inner product would be the vector that is parallel to v, right? So that's basically what we're doing here. And so this sort of very elegantly tells us that the optimal filter is the filter that's proportional to h of f divided by s of f. In other words, if you have some data with known signal, then the right filter to use that is going to give you the highest SNR is basically the signal itself. It's proportional to the signal itself, divided by the noise properties of the data. Yes.
So I think you might go into this later, but how quickly do you start to get penalized if you don't know your signal shape very well? If you draw products, like let's say the pulse profile you assume to be a little bit different, like how quickly can you no longer detect the signal above something?
It depends on how much your signal is changing, based on your assumptions. So, for example, in sort of the gravitational wave context, right? When we do these searches, we usually assume that spins are either zero or that they are maximally aligned. They're like perfectly aligned with the orbital angular momentum. And that's not always true. And when that happens, your signal will change. So you'll penalize yourself in some way. But spins are like a second order, so that they're not going to hurt you a lot. But on the other hand, if you make some incorrect assumption about masses, which in the gravitational wave context are much more important, so then that's going to hurt you a lot more. So it very much depends on like how that's affecting the waveform, and so on.
The best way to get around that, just like in your case, there's a lot of different masses, like big risk.
Yes, and we're going to get to that, right? Okay, so now you might say, Sharan, this is all great. You know, but this is like something that's not going to help me, because you just said that the filter is proportional to the waveform itself or the signal itself, but I don't know what the signal is. So what am I going to do with this, right? What is the point? And so this is where we sort of flip this. Okay, so we say the SNR is optimized by the true waveform or the actual waveform that's in the data. In other words, the true waveform is the one that optimizes the SNR. Okay, so now if you have data in which you don't know what the signal is, you just need to chuck a bunch of waveforms at it, and the one that optimizes the SNR with this, too many animations, I'm sorry, with the filter defined in this way is going to be the one that is closest to the actual waveform, the unknown waveform that's in the data. And what we just proved is basically that this method is, in stationary Gaussian data, this method is going to be the best detection technique that we can possibly hope, modulo how many waveforms you check at the data.
So I'm confused that we need signal to compute SNR, but then we don't know signal. So in order to compute signal, we need SNR. So
yes, so this is why we are saying it's an unknown signal of a known type, right? So we already know what the signal is looking, what the signal morphology looks like.
Is it like theoretical?
Yes, so theoretical or maybe the dynamics is simple. For example, in an exoplanet case, maybe the dynamics of what the light curve dip is going to be like is simple enough that you can model it. Or in with gravitational wave detection, you have general relativity that tells you for like a set of masses and spins of black holes what the waveform is going to look like. So you have some way of knowing what the waveform is, or maybe it's a pulsar, and you understand based on the way a pulsar spins that this is sort of what the signal is going to look like. Or you have some space of signals that you think is appropriate, right? So you gotta know that, and then what you can do is you can draw from that space multiple waveforms, and you can calculate multiple. And for each waveform, you can calculate your optimal filter and calculate an SNR. And what we just proved is that the filter or the waveform that's best fit is going to maximize this thing called the match filter SNR or the optimal SNR.
Thank you.
So that's like So that's where this flip is coming. And so this is just a simple example of something like this. So I have some pretty noisy data. I have a signal. By eye, at least, it's sort of hard to tell what the signal looks like. That there is a signal here. The variance looks almost similar to the noise on the sides, but this orange, this blue trace here is the maximum template or the optimal template, and there are a bunch of orange traces on the back which show other templates. So at this point, I'm gonna pivot and walk you through a notebook which does this match filtering for a simple case. But I do want to ask if people have any questions before that. All looks fine, understandable.
So in the end here, it is mostly noise then, if the signal is so small.
So that's it. Yeah, sorry, this part, unfortunately, it's not it's not showing up super clearly on the screen, but this is, so the white trace is the data, right? And in the top panel, the blue trace is the signal that I've added to the data. Okay. And in the bottom panel, what we're trying to do is do some match filtering and try to actually detect this unknown signal. I don't know what this signal is. I'm not trying to detect it. And that is the blue trace here, is the maximum SNR template. And from the white trace alone, it is sort of hard to see that there is a signal, right? The peaks are not that high. They look basically like the noise on the side at the ends of the box where the signal is dying down. But from the but the optimal but match filtering is still able to pick up and say, oh, hey, there is a signal at the middle, even though it's kind of weak. Yes.
So in practice, is this usually used with some like optimization algorithm, or is it really just it's like guess and check, basically, right? Guess and check and maximize your signal performance?
Yes.
So it's used with this to speed up the computation.
There, yeah. I mean, when people actually, so this is an example of a case of something that is embarrassingly parallel, right? So when people do this in practice, yes, they do use or do this in like with parallel processing, and nowadays like GPUs are being used a lot more also. But yeah. Okay, so let's pivot and talk about how we can do this, how to do match filtering in practice. This is going to be a very simple example that has nothing to do with gravitational waves, and I hope like it actually gives you some understanding of the dynamics behind or the mechanics behind how match filtering works in practice. So what we're going to work with are sine Gaussian wavelets rather than a physical waveform. A sine Gaussian wavelet is basically a sine wave or a cosine wave multiplied with a Gaussian. Okay, and what this does is basically it restricts the Gaussian. It restricts the sine wave, so it doesn't go along. It's not extending to infinity, but it's localized, right? And so there are basically 3 or 4 parameters here. There's T0, which tells you the time at which the wavelet is to be localized, the frequency of the wave, and this tau parameter, which controls how big the localization, how big or how small the localization is. And there is an extra phase term. I'm just going to assume that it's 0 in this notebook, just to make our lives easy. And someone pointed out that the Fourier transform of a Gaussian is also a Gaussian, right? And so in frequency domain, this also looks like a sine Gaussian wavelet. So it has a Gaussian term and this complex wave term, and yeah, it basically sort of looks pretty similar to this. And there is a version of the Heisenberg's uncertainty principle that's actually at play here, where if you notice that tau enters the denominator of the wavelet in the time domain, but enters the numerator of the wavelet in the frequency domain, which means if you make your tau pretty small and try to crush the wavelet in the time domain, you're going to elongate the wavelet in the frequency domain and vice versa. Okay, so let's create some sine Gaussian wavelets in Python. So this is a time domain wavelet. So I have the exponential term here, I have the wave term here, and I multiply them both with some amplitude. Okay. I did not hear. Sorry, there should be an amplitude term here, A, which is present here. So this is, and this amplitude obviously, of course, this tells us how big or how strong the wavelet is. So that's the wavelet in time domain. I'm also defining the wavelet in frequency domain. And the reason why I have these sort of nuns here, I'm going to come back to that in a minute. But this is basically the definition of the frequency domain wavelet that I had in the previous slide. Okay, so let's now I'm going to create. I've written some methods or functions to create my wavelets. Now I'm going to add them to white time domain data. So this is data in which the noise at any point in time is an independent drop from some Gaussian with some noise sigma. And I define for my injection or signal. So this is jargon, but in a lot of gravitational wave parlance, we use the term injection to mean simulated signal. So I'm gonna use that here, but it just means injection, or INJ just means simulated signal. So I'm defining the amplitude, the frequency, the time, and the scale tau of this wavelet. I define what the noise, what the standard deviation of the noise should be, and I create some data. So now I'm plotting the wavelet. So this is what the wavelet looks like in. Sorry, this is sort of what the data looks like in time domain. So the blue traces here are the data itself, and this orange curve here is the simulated signal, the injection that I put in. And in frequency domain, I've also plotted this in frequency domain, where the blue trace is here again is the Fourier transform of the noise, and the orange curve is the Fourier transform of this of the injection. Okay, so now let's do some match filtering. So remember that we defined the SNR as as the dot product between U and H, where U is the template divided by the inner product of U itself. So the inner product itself is defined in this way, right? It's A times B B conjugate divided by the noise. In our case, the noise it's white Gaussian noise. So Sn of f is basically independent of frequency. So I'm just going to drop Sn of f everywhere from here. So what that means is that our SNRs are not absolute, but they're going to be relative SNRs because I'm dropping this term. But that's totally fine. So now we want to do match filtering. We don't know what the waveform parameters are. We also don't know where the waveform is going to be in the data that we have. And by the way, I've created how many seconds of data? I've created 8 seconds of data here at a sampling frequency of 0.01 hertz. So we don't know where the actual waveform is going to be. So what we've done here is so there's something kind of smart that we can do, which is if you take the inner product A times B B conjugate and move the signal around in time domain, then that introduces a phase in frequency domain when you go for your transform. So this is just coming from the fact that let's say you have h of f, which is some h of t times e power 2 pi I t dt, right? So that's h of f. Now, if I introduce some time lag, some lag here, h of t plus tau dt, I can redefine, I can do a change of variables and say, I don't know, x equals t plus tau. That would give me h of x times e power 2 pi I x times e power minus 2 pi I tau dt. This is a factor that I can pull out, right? And so what this basically gives me is h of f times e power minus 2 pi I tau. So if you slide your times, if you slide any signal that you want to take the Fourier transform of around, this in the frequency domain, this basically introduces a phase shift. And so we're going to use this where we say, I don't know what the at what time, what is the time of my signal? Like I don't know where my signal is in the data, but I don't need to calculate the SNR for every point in time. I can just do it for one point in time, and then for every other point in time, I can get my SNR for free because I can just introduce this phase shift. And that is basically what this is saying. So we just need to calculate the SNR for a given template at one point. So far, so good. Any questions? Okay, so this is what this is basically what this is trying to do, where I have some data in frequency domain. I have some templates. I take the dot product of the two, and then I take the inverse Fourier transform, and this gives me the S series for free, as I was pointing out here. And the noise term is simply, so remember the noise term is the inner product of the template with the template itself. So that's the absolute value of the template squared, and then I have an integral for frequency. So this is, yes.
Sorry, you might have said this, but I missed it. Template is what you guess of what.
Yes. Yeah. Yes. Sorry, I should have defined that. Yeah. Template is basically my guess of what the true signal is. And so the idea here is that I'm going to make lots of guesses, and the optimal template or the template that's closest to the true signal is going to be the one that maximizes my signal.
So I think a couple of slides ago you showed a slide like injection and data. So injection I can compare with the
Yes, injection is basically the simulated signal that I'm adding. So no, that's not the template. So there are two steps, right? So I mean, I know what template I know what injection or simulated signal I've added, but here I'm pretending that I don't know what it is, and I'm trying to recover it. So injection is just the simulated signal that we added that we know is the true value. And so we can then go back and check if the recovered optimal template or recovered match filter template is close to the injected template. Does it make sense? Yes.
So you might get this mentioned, I don't know, but how is this different than like chi-square?
With chi-square fitting, it depends on. So in certain cases, both of them reduce to the same thing. But in chi-square fitting, it also depends on what you assume about the noise itself, right? Or like in a lot of cases when people do chi-square fitting, they don't actually really check what the statistics of the noise is. And so if the statistics of the noise is appropriate, then the chi-square fit can be the same as a match filter fit. But the match filter fit is like mathematically we've just shown that it's the optimal fit. Whereas if the noise, for example, is not well represented by a chi-square, like this noise whose variance that you know is not well represented by a chi-square distribution, then it's not going to be it's not going to give you the optimal value. Whereas this is like it's basically guaranteed to give you the value that's optimal. But not always. I'm going to come back to that, some of that later. Okay. Any more questions before I go ahead? Okay. And so now I can calculate the SNR. Okay, so I should come back here and talk about this thing, Einsum or Einstein summation. How many of you are aware of this in NumPy, SciPy? A few hands. So this, it turns out, is a really elegant way to do any sort of matrix products in Python or with NumPy. And Einstein summation, it's basically what it sounds like, right? We are doing Einstein summation. And I guess I should have erased that. You can erase it.
You can also lift the board.
Oh yeah. So Einstein summation is basically you give it. So you give it some formula, and you give it two matrices or two arrays, and it spits out a summation according to the formula that you give it. And A and B can be, they don't need to be two-dimensional or one-dimensional or whatever. They can be any dimensions you want. And this formula sort of tells the thing how to calculate the summation. So let's say this is 4-dimensional, this is 4-dimensional, or maybe this is just 2-dimensional. And you want your product to be a 3-dimensional thing where you summed over, I don't know, the third axis. But you're sort of just only multiplying the other two axes. So you can write your formula here to be something like IJKL and IK IJL. But this formula then says do a product-wise multiplication of the first dimension in A with the first dimension in B. Do a product-wise multiplication of and then do a product-wise multiplication and summation. So of the third dimension in A with the second dimension of B, but leave the first dimension unsummed. So we are just doing a product, an element-wise multiplication and leaving the first dimension alone. Whereas with the k-weighted index or with the third dimension, we are doing an element-wise summation, element-wise product, and also summing, and leave this fourth dimension and the second dimension of it. And does that make sense? So there, the documentation I found on the documentation on this is very confusing, but this is basically the gist of it. Is you tell it what to do with each dimension, and this is actually very powerful. So if you have, if you're dealing with arrays which are many dimensional, and you want to multiply them, and maybe you want to do a dot product on certain dimensions, but only do an element-wise product on other dimensions. This is going to be much faster for you than using like NumPy, for example. And the nice thing about this is this also exists in like QPy or JAX or all of these other platforms. So you can just write equivalent code and it will work on any of these faster alternatives to NumPy. So that's basically what I'm doing here. My template will have, as you will see, is many dimensional, whereas the data itself only has is like one dimensional, and the number of bins the data has is basically equal to the number of frequency bins I have in my Fourier transform. And so I'm using einsum here to do a very nice multiplication. That's in this case, it's probably not going to be much quicker than using NumPy dot. But if this was like 2-dimensional, for example, or 3-dimensional, that would end up being faster. Okay, so we also have to pad our data before we do this for some good behavior. I'm not going to go too much into detail on this. We are also going to come back to this when we in our next notebook on gravitational waves. So you all can take a look. I'm going to skip ahead. So now we've written a method to calculate the SNR. Let's actually do this, and let's actually create a template bank and calculate the SNR time series and see what the optimal template is. So, oops, this cut off a little bit, which is unfortunate. Let's see. Okay, so just to go back again, this was the SNR time series method that we had just created. So now I'm going to create my template. I'm going to create my template bank to have 10,000 waveforms in the template. So that's this quantity here. And what I'm going to do is I'm going to randomly sample in my amplitude space, in my frequency space, and in my tau space. And I'm going to I have some lower and higher bounds, which are completely arbitrary that I've set here. And for each of them, I'm going to draw 10,000 samples in these space. And so I have 10,000 templates. And I don't need to sample in T0 space, which is the location of the wavelet itself, because this nice property of the Fourier transform that if I just take the Fourier, if I just calculate the SNR at one point, then I can just take its inverse Fourier transform basically and calculate the SNR time series. So now I'm calculating the Fourier transform of the data itself. So of course we want to work in frequency domain. This is where I'm padding the data. It's basically adding some zeros on the side for some good behavior with how FFTs work. Where if the number of data points that you're transforming, that you're taking an FFT of is a not a multiple. What do you call it? It's like 2 power n. Then your FFTs are much faster. You have to window the data to prevent ringing. So I'm multiplying this with a cosine window called a Tukey window. And I'm generating my template here. I'm generating my template directly in the Fourier domain because for this sine Gaussian wavelets, we have the nice property that I can write analytically out what the signal in the Fourier domain looks like, right? And that is, if you look back, if you go back, I promise that I'm going to talk about this. This is why there are these nuns here, because T0 here is just one number, as you can see. I'm just using T0 of 0 because I only need to calculate the wavelet once. Whereas everything else, my frequency space and is a different array. It's the number of frequencies I have. So all of these are these two are basically the same size, but all of the others are different sizes. And what this is doing is it's allowing quick broadcasting of these arrays of different sizes, so that I can calculate my template back, which is now going to be size 10,000 times the number of bins I have in my Fourier transform. So I do that, and then I calculate the SNR time series. And so I calculate the SNR time series now for each template in the template bank. So I have SNR here is basically an array of times 10,000. Now I can calculate the optimal SNR at every point in this time series, and I can calculate the optimal arguments that allow me to maximize that SNR. In the next panel, I'm going to plot this. So this is the optimal SNR as a function of time. This is the maximal SNR as a function of time, and this point here is the represents the template with the maximum SNR. So this is going to be the optimal template, at least as far as the resolution of our template back comes. And this the lower panel shows the reconstruction of the optimal template. So the blue is the recovered template, whereas orange is the injected template, or the simulated signal. Of course, it's not perfect because there is some noise, but it is pretty close. And one other note, as I said, we dropped in all of our calculations this S of F, which means that our SNRs were not real SNRs, but only proportional to the real SNRs, which is why the number here is pretty low. So it doesn't actually have an SNR of 0.003. It's just SNR of 0.003 multiplied by this term that we are omitted. Okay, so that was that's a quick demonstration of match filtering. This recovery is not great because the wavelet basis has a bunch of degeneracies, which means that different wavelets with different parameters can look very similar. But with gravitational wave signals, as you'll see in a little bit, these optimal peaks can be quite narrow. And yeah, any questions? Yes.
These plots kind of confuse me a bit. So
Okay.
you have your data, your signal is a function of time, and you have a set of templates that are defined on the grid, and you're finding in that grid this way, you're finding which template is the maximized.
Yes.
Yeah.
Yeah. So we are finding. So what we're doing basically is, let me go back to this, right? So okay. So I'm placing a bunch of templates here. What's happening under the hood is I'm placing a bunch of templates here, 10,000 templates here, calculating the optimal SNR, moving it slightly, placing 10,000 templates here, again calculating the optimal SNR, again doing it, again doing it, again doing it, again doing it. Oh, here the optimal SNR is gonna start increasing here because we're getting closer to the signal. And then as we continue, the SNRs will drop again. And so it is that which is being plotted here. Does that make sense?
Yeah. But if you're fitting 10,000 templates in one small region.
No, we're not fitting 10,000 templates. We are calculating the SNR for each of these 10,000 templates here, or wherever, and asking, okay, what is the maximum SNR that I get here? Okay. And then what is the maximum SNR that I get here? What is the maximum SNR that I get here? Of course, we are not actually doing the time slide because of the nice property of the Fourier transforms that I was talking about. But under the hood, like mathematically, that is sort of what's happening.
So why do you need to do a time slide? Why not have 10,000 templates that you fit everything with, like the whole data, use the whole data, and then just have one signal to noise ratio?
Well, yes, you can do that. You can do that. You mean also like just basically sample in time, right? Is what you're saying. You can definitely do that, but the problem is when you're applying this for real signals, you don't want your parameter space that you're sampling over to be too high dimensional, right? So if I have 10,000 signals here, but 10,000 signals in like a realistic application are going to be, it's going to be pretty small. You want your template bank to be, at least a few million signals big, and as you increase the dimensionality of the space, the coverage of this template bank in your high dimensional space is gonna drop as you increase the dimensionality. So you want to make sure that you throw a million signals, but you also want to make sure that that the parameter space that you're sampling over or drawing grids over is going to be small, so you actually have dense coverage. Make sense?
Yeah.
Okay.
You might have already explained it, but I'm just not wrapping my head around why the recovered signal has a higher amplitude than the injected signal. That's a result of the noise. Yeah, basically. Noise. I mean, if you rerun this, it's probably going to be the other way around next time with a different seed. Any other questions? Okay, maybe we should take a break and come back.